Welcome to Calculus. Today we'll investigate using logarithmic differentiation to differentiate a function with respect to x. And the classic type function that we're looking at where logarithmic differentiation is very helpful is when I've got some kind of fusion between a polynomial and an exponential function. So here we've got an example, y equals 3x to the power of 4x. So you'll notice that x is both in the base and in the exponent. So to use logarithmic differentiation, the nice thing about that process is that it follows the same steps. Our first step is I want to take the natural logarithm of both sides of the function. I'll put this step out to the side. Take natural logarithm of both sides of the equation. So we'll take that first step here. I'm going to start by taking the natural logarithm of y on the left. And on the right, the advantage of taking natural logarithm is that it will take that power of 4x and bring it down as a coefficient. So I'll bring that 4x down, and the natural logarithm's now got the argument 3x. Again, it would have been written there as an exponent, but then by logarithm rules, that 4x comes out front. Once we take the natural logarithm of both sides, our second step is to perform implicit differentiation to the function. We want to perform implicit differentiation to the function. So we'll apply the differentiation on both sides. So we're going to differentiate with respect to x of ln y, also of the right side, 4x times natural log of 3x. So once we simplify that differentiation, here on the left, the derivative of natural log of y, or we could think that's just u, would be 1 over u. So I'll, in fact, just use 1 over y. And that leaves us with dy dx, according to the chain rule. We'll come back to that side. Remember, with implicit differentiation, we're going to have to solve at some point for dy dx. But let's differentiate this right-hand side. So now the derivative with respect to x of 4x times natural log of 3x, it's a product, so we need to employ the product rule. So that's going to be 4x, that first factor in the product as it is, and times the derivative of the natural log of 3x. So that's going to be 1 over 3x. But then recall, I need to take the derivative of that composed function 3x according to chain rule. And that would just be that factor of 3. And then plus the second factor unchanged, natural log of 3x, times the derivative of 4x, my first factor, which is just 4. So we've taken derivative of both sides using implicit differentiation. Now I want to solve for dy dx. So I can do that pretty quickly by multiplying each side by y. That'll cancel y on the left. And notice that solves for dy dx. On the right side, I'm going to also multiply by y, and I'll put brackets to show that it needs to be distributed. So my next step has dy dx alone on the left, that's solved. And where I'm seeing y, I want to make a substitution, because I really don't want this to be a multivariable function. I just want it to be in terms of x. So if I go back to the beginning, I notice that my original y function is 3x to the power of 4x. So I want to substitute that in for y. And that's really the third step in our logarithmic differentiation. So we'll write the substitution. So y is 3x to the power of 4x. And then I'm gonna write the rest of what we had here, and we'll combine some numerators. So 4x times 1 times 3 would be 12x over 3x plus 4 times the natural logarithm of 3x. So before we finalize everything, I'll put this third step here, is I need to substitute the variable y with the original function in terms of x. So we've done that step already. What we need to do now is just to kind of simplify and reduce. So I do see I have a cancellation. 12 divided by 3 is going to just be 4. And x divided by x cancels entirely. And so our final answer here can be, if we just reduce down to that simplified y prime form, equals 3x to the power of 4x times 4 plus 4 times the natural log of 3x. And I'll box that as complete. So that was a fairly straightforward example where we can use logarithmic differentiation for that specific type function where it's an x base to an x exponent. Let's take a look at an example that involves a product. So here I've got the function y equals quantity 2x cubed minus 3 cubed times quantity 5x to the power of 5 minus 2 squared. The advantage of using logarithmic differentiation for this example is that I can use the logarithm expansion rules to make this product easier to differentiate. So we'll employ our 3 steps. Our first step, recall, is to take the take the natural logarithm of both sides. So we'll do that first. The natural logarithm of y equals the natural logarithm of this right-hand side. So I'm going to put a bracket over it, and I notice a few things. It's a product, first of all, so I can split this using the expansion rules for logarithms into a sum. So it's natural logarithm of the first factor, 2x cubed minus 3 cubed, plus the natural logarithm of the second factor, 5x to the power of 5 minus 2 squared. But I could even take it a step further. I could take, according to the same rules for logarithm expansion, I can bring those powers down as coefficients in front of the logarithm. And so the final expansion would give me a coefficient of 3 on the first term, coefficient of 2 on the second term. And at that point, we would let these powers go. So there I've got the expanded form. That's the advantage of using the natural logarithm there. Now I want to implicitly differentiate both sides. So I'm going to put dy dx on both sides of the equation. So again, I'm going to start there with the left side. A lot of times that looks the same because typically our functions start y equals blah, blah, blah in terms of x. So again, the derivative will look like 1 over the argument, which is y, times dy dx. And then we can begin taking the derivative of each of these terms on the right. So the derivative of 3 times the natural log of 2x cubed minus 3 is going to be 3 times the quotient 1 over that argument 2x cubed minus 3. But since that's not just x, it's another function, 2x cubed minus 3, I have to use the chain rule and take the derivative of the composed function. So that's going to be 6x squared plus 0 And then we'll do the same for the second term on the right. So I'll take its derivative implicitly. So that's going to be 2 times the quotient 1 over the argument 5x to the power of 5 minus 2. And again, since that's a composed function, I will use chain rule to take its derivative as well, which is 25x to the power of 4 plus 0. So on the left-hand side, I'm ready to solve for dy dx by multiplying by y. That cancels there on the left. And so all we're left with is the derivative of y with respect to x. So that part's pretty much complete. And then on the right-hand side, I also put that y with large parentheses to say I need to distribute. So my next step is going to look like dy dx, which I'm going to call just y prime for simplicity. And then where I have y, I need to go back and put the original function. So remember, y equals this product of two polynomials. So I'm going to substitute back for y that right side, 2x cubed minus 3 cubed times 5x to the power of 5 minus 2 squared. And again, that's substituting y back. And now I'm going to build that simplified form of this right-hand sum. So that first one, I've got numerator values of 3 times 1 times 6x squared. So that's going to be for us 18x squared all over 2x cubed minus 3. And then the second product here, which is again a quotient, so it's numerator 2 times 1 times 25x to the power of 4, which is going to be 50x to the 4th over 5x to the 5th minus 2. So at that point, I do want to keep reducing if possible, and I'm going to distribute this function, our original function, to each of these fractions. And I notice that part of it's going to cancel because it shares a term in the numerator and the denominator. So my next step is going to look like y prime equals, so I'm going to write them out and then we'll make the cancellation. I'll put the 18x squared first. And then I'm going to have 2x cubed minus 3 cubed, 5x to the power of 5 minus 2 squared, all over 2x minus 3. So I see that cancellation right there. So it's going to leave a power of 2 in my numerator. And at that point, the denominator's canceled out. And then for my second distribution, I'll put 50x to the 4th first. And then that same original function, 2x cubed minus 3 cubed times 5x to the power of 5 minus 2 squared, all over 5x to the power of 5 minus 2. So again, there's a cancellation above and below with 5x to the power of 5 minus 2, and it'll leave just one power of 1 in the numerator. So now we're ready to reduce that down to a single level. We don't have any more fractions. So that's going to give us 18x squared times 2x minus 3 out of the power of 2 times 5x to the power of 5 minus 2 squared plus 50x to the power of 4 times 2x cubed minus 3 to the power of 3 times 5x to the power of 5 minus 2. So what I want to look for now is, can I factor anything out of both those two terms? If I could write this as a product instead of a sum, that would be advantageous. So I see that 18x squared and 50x to the power of 4 share a common factor of 2x squared. So I'm going to factor that out. I'm also going to factor out any of these common binomials. So I see that the first term there has 2x minus 3 to the power of 2, and the second term has that same one to the power of 3. So the common factor would be 2x minus 3 squared. So again, I'm factoring that out to the left. The last piece that's here for us is going to be, if I highlight it, this common factor of 5x squared to the power of 5 minus 2 squared. And I've got the same binomial, but it's to the power of 1. So then my common factor would be that 5x to the 5th minus 2 just to the first power. So then I do want to write out what's left after I factor out that common factor. So let's write what's left after that factorization. So from the first term, if I divide 18x squared by 2x squared, I'd have 9 left. And then I've factored out all of what's highlighted in blue and everything except one of the binomials, 5x to the 5th minus 2. I had factored out just one of those. Now for the second term there, so in green, if I divide out 50x to the 4th divided by 2x squared, that would leave me with 25x squared. And then I've factored out the power of 2 on that blue highlighted one, which leaves me 1 because that's got the power of 3. So 2x cubed minus 3. And that completes that. So my final version here, y prime, is going to be 2x squared times 2x minus 3 squared times 5x to the power of 5 minus 2. And then I'm going to distribute some stuff up above our last step, and then we'll combine it in our final step. So 9 times 5x to the 5th is 45x to the power of 5. 9 times minus 2 is minus 18. 25x squared times 2x cubed is plus 50x to the power of 5. And 25x squared times negative 3 is minus 75x squared. So we'll put that in descending order of exponents. I see I got some common terms there, 45x to the 5th plus 50x to the 5th. That's 95x to the 5th minus 75x squared minus 18. And that completes the derivative there of that product. Definitely we could use this logarithmic differentiation for products. It's also useful for quotients, since we can convert quotients using logarithmic rules to differences. But we'll let these two examples suffice. Thanks for joining for this investigation of logarithmic differentiation. See you soon.